Hello everyone. In today's lecture, we will learn edge connectivity and Whitney's theorem. We will see the definition of edge connectivity and get a property of two connected graphs, which is called Whitney's theorem. We have known some graph operations, including deleting a vertex and deleting an edge. But there is a difference between deleting a vertex and deleting an edge. To delete a vertex is to delete this vertex and all the edges incident to this vertex. Because every edge has two ends, if one end is deleted, the edge will no longer exist. To delete an edge is to delete only this edge. We do not delete its ends. Let's take an example. In the left graph, to delete the vertex x is to delete x and the edge vx and xy. This is to delete the vertex x. But to delete the edge vx is delete only this edge. In the last lecture, we have learned vertex connectivity. In this lecture, we will consider its analogs, which is edge connectivity. A vertex cut is a connected graph G is a vertex set such that G becomes disconnected after deleting the vertex set. The corresponding definition here is a disconnecting set. A disconnecting set is an edge set such that G becomes disconnected after deleting this edge set. So the first definition is a vertex set and the second definition is an edge set. If we delete it, the graph G will have more than one component. A k-connected graph is a graph such that every vertex cut has at least k vertices. The corresponding definition of k-connected is k-edge connected. A k-edge connected graph is a graph such that every disconnecting set has at least k edges. Thus, a k-connected graph is if you delete any k-1 vertices, the graph is still connected. And a k-edge connected graph is if you delete any k-1 edges, the graph is still connected. The next pair of very similar concepts are connectivity kappa G and edge connectivity kappa prime G. The connectivity kappa G is the minimum size of a vertex cut. The edge connectivity kappa prime G is the minimum size of a disconnecting set. We have also learned a cut vertex. If you delete a cut vertex, the connected graph G will become disconnected. A cut vertex is also a vertex cut, but usually a vertex cut is a set of vertices which may have many vertices, while a cut vertex is only one vertex. The corresponding definition is a bridge. A bridge sometimes is called a cut edge. A bridge is an edge which can disconnect graph G. Let us now formalize these definitions again. Here we consider only connected graphs. A disconnecting set of edges is an edge set F such that G minus F has more than one component. So a disconnecting set is an edge set which can disconnect G. A graph is k-edge connected if every disconnecting set has at least k edges. So if a graph G is k-edge connected, then any k-1 edges cannot disconnect G. The edge connectivity of G, written by kappa prime G, is the minimum size of a disconnecting set. One edge disconnecting G is called a bridge or a cut edge. Let's see the graphs below. In the left graph, the bold black edges form a disconnecting set, because if you delete the bold edges, this graph has more than one component. In the middle graph, the two red edges also form a disconnecting set. If you delete the red edges, the vertex in the lower right corner cannot connect the other vertices. In the right graph, the green edges also form a disconnecting set. So what's the edge connectivity of this graph? The edge connectivity is 2, because if you want to disconnect this graph, you have to delete at least 2 edges. The minimum size of a disconnecting set is 2, so is the edge connectivity. A definition similar to vertex cut is the disconnecting set, but we do have a definition of edge cut. Given two vertex sets S and T, the notation ST with square brackets denotes the set of edges having one endpoint in S and the other in T. An edge cut is an edge set of the form S and the complement of S with square brackets. Here, S is a non-empty proper subset of VG. The complement of S is the set of all the vertices which belong to VG but not belong to S. That is to say, the vertex set can be partitioned into two sides, S and S bar. An edge cut is a set of all the edges with one end in S and the other end in S bar. The following is an example. In the left graph, the red edges form a disconnecting set, but not an edge set. In the middle graph, the vertex set has been partitioned into two parts, S and S bar. All the edges between S and S bar form an edge cut. In the right graph, the red edges also form an edge cut. This is because the vertex in the lower right corner is one part. All the other vertices make up the other part. The two red edges are all the edges between the two parts. We see that a disconnecting set may not be an edge cut, but an edge cut must be a disconnecting set. Now we calculate the edge connectivity of some special graphs. for a complete graph Kn, its edge connectivity is n-1. Because if we choose a vertex v from this complete graph, v is incident to n-1 edges. After deleting the n-1 edges, which are incident to v, the graph is disconnected with v as an isolated vertex. To disconnect Kn, you have to delete at least n-1 edges. So its edge connectivity is n-1. Recall that its connectivity equals its minimum degree equals n-1. So the three parameters are exactly equal. The next graph is a complete bipartite graph KMN. The figure here is a complete bipartite graph K35. Consider the red vertex in the upper right corner. There are three edges incident with the vertex. These three edges form an edge cut. So it's easy to see that the edge connectivity of K35 is 3. Thus, for KMN, where m is less than or equal to n, its edge connectivity is m. Also, its connectivity and minimum degree are m. We have two remarks. The first one is, if G is k plus 1 edge connected, then G is k edge connected. This is easy to understand. The second one is, an edge cut is a disconnecting set, but a disconnecting set may not be an edge cut. A disconnecting set contains an edge cut, but it can have more edges. Now we have two other graphs. For the first graph, its edge connectivity cup prime G is 3, because these three edges disconnect the graph. And if you delete any two edges, the graph is still connected. Its connectivity cup G is 2, because these two vertices disconnect the graph. And if you delete any single vertex, the graph is still connected. It's easy to check that its minimum degree is 3. For the second graph, its edge connectivity cup prime G is 2, because these two edges in the middle disconnect the graph. And if you delete any single edge, the graph is still connected. Its connectivity cup G is also 2, because these two vertices, these two vertices disconnect the graph. And if you delete any single vertex, the graph is still connected. It's easy to check that its minimum degree is 3. Some students may have discovered such a fact. For any graph, its connectivity is less than or equal to its edge connectivity, which is less than or equal to its minimum degree. This result is first found by Whitney in 1932. This theorem tells us the relationship between connectivity, edge connectivity, and minimum degree. Kappa G is less than or equal to kappa prime G less than or equal to dot G. The second inequality is easy to prove. The edges incident to a vertex V of minimum degree form a disconnecting set. They disconnect V from the other vertices. Hence, kappa prime G is less than or equal to dot G. It remains to show the first inequality. Kappa G is less than or equal to kappa prime G. Suppose that the size of G is larger than 1, and the set of edges between S and the complement of S is a minimum edge cut. Having set kappa prime G, we can take the bottom picture as an example. This is not an appropriate example because the three edges in the middle form an edge cut but not a minimum edge cut. What we need to learn now is that how to get a vertex cut from an edge cut. Every edge of the cut has an end in S. The two ends form a vertex cut. For any edge cut, do all the ends of the edge cut form a vertex cut? The answer is correct most of the time, but sometimes it is wrong, because sometimes every vertex of S is an end of some edge in the edge cut. Then deleting the ends means deleting all the vertices of S. In this case, the whole S was deleted, while the remaining graph is still connected. So the proof is divided into two cases. The first case is every vertex of S is adjacent to every vertex of the complement of S. The second case is there exists X belonging to S, Y belonging to the complement of S, such that X is not adjacent to Y. In the second case, we don't consider all vertices of S that have neighbors in S bar. This is because maybe every vertex of S has neighbors in S bar. Instead, we consider all neighbors of X in S bar and all the other vertices of S that have neighbors in S bar. The purpose of this is, after deleting these vertices, both S and S bar are not empty. Next is the formal proof. If every vertex of S is adjacent to every vertex of S bar, then kappa prime G equals the set of S times the set of S bar equals S times G minus S. As S increases, this expression first increases and then decreases. This expression is minimized at S equals 1. By definition, kappa G is less than or equal to the minimum degree which is less than or equal to g minus 1. In this special case, we have proved g minus 1 is less than or equal to kappa prime g. So the inequality holds. Hence, we may assume there exists x belonging to S, y belonging to S bar, such that x is not adjacent to y. Let T be the vertex set consisting of all neighbors of x in S bar, and all vertices of S except x that have neighbors in S bar. This is a small trick. For each edge of the edge cut, if the endpoint in S is not x, then we choose it as an element of T. If the endpoint in S is x, then we choose the other endpoint as an element of T. Deleting T destroys all the edges in the cut S bar, but does not delete x or y. So T is a separating set. Now, by the definition of T, we can injectively associate at least one edge of the cut to each vertex in T. This is to say, the size of T is less than or equal to the size of the edge cut. Thus, kappa G is less than or equal to T is less than or equal to kappa prime G. Now we have the final result. Kappa G is less than or equal to kappa prime G is less than or equal to delta G. Now we turn to another theorem given by Whitney. We need this definition: eternally disjoint paths. Two paths are eternally disjoint if neither contains a non-endpoint vertex of the other. That is, they do not share a common eternal vertex. The graph below is 3 eternally disjoint xy paths. This is a negative example. Two paths from 0 to 7 which are not eternally disjoint. They have a common internal vertex 6. The length of the shortest path from U to V is called the distance from U to V, denoted by DUV. So here, the length from 0 to 7, the distance between 0 and 7 is 3. This is a Whitney's theorem. A graph G having at least 3 vertices is 2 connected if and only if every 2 vertices UV is connected by a pair of internally disjoint UV paths in G. This is an important feature of 2 connected graphs. The sufficiency is easy to explain. When G has 2 internally disjoint UV paths, deletion of one vertex cannot separate U from V. Since this is given for every pair of vertices UV, deleting any vertex cannot separate any 2 vertices. So G is 2 connected. The condition is sufficient. For the necessity, we suppose that G is two connected. We need to prove that every pair UV is connected by a pair of internally disjoint UV paths. We prove by induction on the distance of UV, DUV, that G has two internally disjoint UV paths. When DUV equals 1, this means U and V are adjacent. UV is an edge of G. Because cap prime G is greater than or equal to cap G is greater than or equal to 2. After deleting the edge UV, the graph G minus UV is still connected. Note that this UV with round brackets denotes the edge UV. A UV path in G minus UV is internally disjoint in G from the edge UV itself. Hence, UV is connected by a pair of internally disjoint UV paths in G. The basis step is done. For the induction step, we consider DUV equals K greater than 1 and assume that G has internally disjoint XY paths whenever the distance dxy is greater than or equal to 1 and less than K. To use the induction hypothesis, we need to find two vertices whose distance is K minus 1. So we let W be the vertex before V on a shortest UV path. We have DUW equals K minus 1. The distance between U and W equals K minus 1. And hence, by the induction hypothesis, G has internally disjoint UW paths P and Q. Let's use this graph to make a better illustration. The distance from between U and V is K. We cannot use the induction hypothesis, but let W be a vertex before V on a shortest UV path. Because DUW equals K minus 1, now we can use the induction hypothesis and hence we can find internally disjoint UW paths P and Q. This is by induction hypothesis. But remember that we need to find internally disjoint UV paths because G is two connected. G minus W is connected. Any two vertices are connected in G minus W. So G minus W contains a UV path R. G minus W is connected. G minus W contains a UV path R. Now we have three paths, two paths P and Q from U to W, and another path R from U to V. If this path R avoids P and Q, we are finished. URV is a path, and U following the path P to W and then to V is another path. But R may share internal vertices with both P and Q. R may share internal vertices with both P and Q. What do we do in this situation? A common technique in graph theory is used here. Let X be the last vertex of R shared with P or Q. Then we can find two internally disjoint paths. The first one is UPXRV. The second one is UQWV. The proof is done. Let's see the formal proof. Let X be the last vertex of R belonging to P union Q. Without loss of generality, we may assume X belongs to P. We combine the UX subpath of P with the XV subpath of R to obtain a UV path internally disjoint from another path Q union WV. In the last part, we have such a corollary. G is 2 connected, and the order of G is greater than or equal to 3 if and only if every two vertices in G lie on a common cycle. From Whitney's theorem, we know that every two vertices in G is connected by a pair of internally disjoint paths. The two paths can form a cycle, so each pair of vertices lies on a common cycle. This is a necessary and sufficient condition. Thanks for watching this video. See you next time.